Cool. Hello, everyone. This is me, who's going to take you on a perilous adventure. That's not the right attire for fighting monsters. Cool. Okay, that's better. So on that note, I will give a content warning that there are some PG-13 images of fantasy violence of Hydras. But with that being said, this adventure first starts with my mum, who really likes giving me gifts. And one day she called me saying that she wanted to give me a wallet. And so I looked at my wallet sitting on my desk, worn and unused, and I realized I don't really use my wallet anymore. Because in today's digital world, all the things that a wallet would normally hold are now on our phones. But now I had a problem, because I would like a wallet, since in some rare cases, it's still nice to have one. Maybe you don't have your phone and you need some spare cash, or you need a paperclip to eject your SIM card. And so I thought, why not ask for a very slim, minimalistic wallet and design a solution myself by making my own custom utility card that I could put in this wallet to hold whatever I needed. In fact, I could laser cut one out at my local makerspace, so it shouldn't be that hard, right? Now, some of you may be asking, what's a laser cutter and how do you use one? Well, you've probably heard of a 3D printer that prints things additively to make something. A laser cutter is kind of like the opposite, but in 2D. It makes something by cutting away from material rather than adding. Okay, but how do we actually print to one? Do we just press Ctrl-P? Well, yes, but that would be like sending a 2D image to a 3D printer. It just wouldn't know how to print upwards. And similarly, a laser cutter needs to know precisely what path to cut along, and it can't figure that out from just a photo. Instead, we need to give it some instructional code. But how? Software. You didn't see that coming, did you? There's a couple of ways, actually. There's some software that's made for cases like this, like Rhino 3D. But really, anything that produces some kind of path to follow will work, like SVGs or scalable vector graphics. And there are some tools like Adobe Illustrator which will let you make these and create shapes and lines of various widths and colors. But both Rhino and Illustrator are paid and don't run on Linux. And so instead, I opted for Inkscape, which is essentially the free and open source version of Illustrator. And so I sat down and spent a night both designing and figuring out how to use Inkscape. Actually, many nights before I was left with this final design, which I was so happy with. And so I adventured to the makerspace, found some scrap materials, loaded up my design, pressed start, and it worked. But I had a few issues, like why didn't some things get cut? And how am I going to be able to figure it all out when it took so long to design and cutting is so out of my way? It was at this point that I realized that I'd be starting my adventure of facing this Hydra, and the first of this Hydra's head that I faced was my complex tools and design. You see, I'd invested so much time into quickly designing something without ever stopping to look at it from afar. And then, when the inevitable unknowns appeared, like some lines not cutting, my design was just too complex for me to be able to figure out what the root cause of the problem was. And I think this can be analogous to when I've designed some piece of software quite quickly to try and make it all work. It was perfectly fine when I was trying to figure out what I was doing, but at some point I needed to stop and design from scratch with an idea of what I was trying to achieve. The second of this Hydra's head that I faced was in the slow and iterative process in going from design to reality. I, for one, don't have the tens of thousands of dollars, or frankly the room, to own a laser cutter at home so I can do quick tests in my own time. And even at the makerspace, I'm either spending valuable time where I could instead be testing, editing the many features of my design, such as making a circle like this to be larger, which required using Inkscape to manually tweak and move all the lines to be precisely the right spot, or I'm waiting for the laser cutter to print things most of which aren't even my own. And maybe this sounds familiar in programming. There's often many slow or cumbersome processes like executing a series of commands to run tests and compile them. And so similarly, it would have been helpful in these situations for me to invest some time into writing tools to assist me that would ultimately compound and save me time in the future. And so with those two challenges, I set alight my sword to slay this Hydra with a tool that I knew best, Python. But how and where can Python help us here? Well, by using Python to create my design, I could make functions that take in all the parameters that I would need to change and instantly spit out a new design. And so if the laser cutter will cut given an SVG, and SVGs are really just strings of text, then we could easily conjure them up with Python. For example, SVGs are made up of some basic elements, like a rect, which lets you define the width and the height, along with its top and left position, as well as the color of the stroke width, and the shape fill. And now, while shapes and all the properties that can be set are great, the real fun starts with path elements, which let me define a custom path that the laser cutter can follow. For example, I'll first define an empty path with an empty draw command, and then I'll use the M command to give it a starting point at a position 2, 1 on an XY plane. And then I can specify where the point moves to or how it gets there by using the L command to create a straight line to another point. Or I can use a lowercase l to create another line to a point 1 unit relatively away from the last position. And then when I don't want to draw lines, I can also move 1 unit underneath using the lowercase m command. And then I can draw a line vertically or horizontally. And there's even some commands like Q, which have some funky maths behind them to get some nice curves, but that's a topic for another talk. And finally, we have Z, which moves back to the last starting point, closing the path if it's open. Remember how I mentioned that lowercase commands act relatively, as opposed to uppercase commands that act absolutely? This is great because if I change all of the commands to be relative, then if I ever need to translate the location of this path object, I can do so very easily by just changing the start coordinate. Okay, so how can I use this to create these rulers in my design? Well, let's say that I wanted to make a function that would create a ruler for a given length and a starting position, like the one on the right. Well, I'll first define a path list, which I'll initialize with a function call at a starting x and y coordinate. And I'll define that as a non-relative move command using capital M, giving me this first point here. Then I'll use a for loop to iterate over all the units for the length of the ruler. And then for each length, I'll call a function to draw a line, which I'll define as using the v command to draw a vertical line of a certain length, followed by z to go back to where it started, giving me my first line. Then I'll follow that with a move function, which I'll define using the m command to move relatively by a unit, moving me to the point where the next line will be drawn. And then finally, I return the entire path joined by spaces. Now we can generalize this code to do things like skip some starting values with an if statement, add another variable to change which direction the lines are to be drawn in, or change the line function to allow for a number to determine the length. And so if I define that function to make the lines be longer when they're even, I can then print the output of my function, which gives me a path of a ruler. Great. But what about more complex shapes, like this circle with degree markings that takes forever to change? Well, I could sit down and calculate the maths to do it, or I could just ask ChatGPT. And here I ask it, please write Python code that generates lines around a circle of a given radius at the given degree intervals using an SVG path. And it goes, certainly. And here's the code that it generated. It looks pretty good. But when I ran it, it wasn't quite right. So it probably won't get it right the first time. But if you ask it again, being more descriptive, it works. And that's great, because my job's done. That being said, it's probably worth mentioning that these are just basic examples to give you an idea of how we can make and use these commands But if this is something that you want to try, don't be like me and regret not using libraries to do this for you, such as draw SVG or svg.py. But now with all this, I could very easily create functions to recreate my initial Inkscape design, but this time programmatically using Python, which will make my editing process much faster and more predictable now that I can specify and play around with the key dimensions. Okay, so now that the file is designed in a programmatic way that allows for quick changes, everything should be good, right? Yeah. The next Hydra head that had appeared was from not researching before designing. Remember earlier how I said that laser cutters cut? Well, you see, they don't only cut. They can do different things based on the color of the path that you give them. And so while red and magenta tell the cutter to cut, blue and cyan tell the laser to use less power or a different speed, so that it scores instead of cutting right through the material. And finally, there's this engraving option, which turns up the speed, turns down the power, allowing for etching of anything that isn't a line, kind of like a normal printer. Now, it would have saved me some time to know these colors before designing, but now since I'm programmatically approaching this problem, I can solve it easily using SVG styles, letting me easily swap the colors to what they should be. And I find this similar to software, where it's good to ask myself, have I researched my tools and libraries to understand their requirements so that I don't make assumptions before using them? Or have I kept my design modular to account for unexpected issues so that it can be easily updated? But alas, these heads just kept appearing, but this time in reality. You see, I had gone to Wikipedia to find that the size of a coin is 20.5 millimeters in diameter. And in theory, a circle that fits a coin should be 20.5 millimeters. But in reality, when I cut that circle out, the coin will either not fit or be too loose. Why? Well, in the real world, coins have been everywhere, and they're not going to be freshly and perfectly minted. Like this one is 20.38, and if we rotate it, it's now 20.28. That's not a circle. So while in theory a coin is 20.5 millimeters, but in reality it isn't, in software I could theorize that linked lists might give the fastest solution, but in reality that doesn't mean anything when hardware gets involved and optimizes for arrays to be faster instead, with of course the easiest way to know that being measuring. Now, although I had learned about tolerances and then I should measure twice, cut once, and then test against real-world cases, I still had a problem, as my coin holes were still the wrong size. Why? Well, this is due to one unexpected property of a laser, and that property is its width. If you think about cutting, you might normally think of scissors, which kindly ask the particles to separate and never see each other again, but that's nothing compared to a laser cutter, which burns these particles out of existence. And thus I learned I need to understand how my tools work. And similarly in programming, what exactly is a library doing? How does it use memory? Could it cause memory leaks? And while I had solved my issue of assumptions, I now had to figure out how to best test them. In software, unit tests are often a common way of quickly testing some functionality. But in the real world of laser cutting, where the whole laser cutter process will always take some time, I could instead test multiple components at once, like cutting out sizes of circles in one go to find out what the right tolerance should be. Another reason for this is because testing my entire design can be slow. Like, it can take 3 minutes just to cut out the front portion of this card. But while I had solved the problem of testing quickly, I was now faced with a new testing problem. This hole at the bottom wasn't there before. So how did that happen? Well, part of my design in my card requires some depressions to fit in thinner objects like a paperclip. But how can a laser cutter do that if it can only either cut or engrave? Well, one option is to change the settings of engraving such that it engraves multiple layers to get the depth that we desire. But a laser cutter has no knowledge of depth. Instead, I needed to determine this through good old trial and error. And while I may have gotten it right in theory and right on one side, I never tested this kind of engraving from both sides. And so with a thin enough material, I sure enough cut right through. This showed the importance of testing my design as a whole, even if it's slow. Like how in software, there's integration tests that check that things work when put together, even though they might work alone. As you can tell, I'd done a lot of testing. Unfortunately, it was a lot of ad hoc testing, completely lacking in documentation whatsoever. So even after getting successful results, I'd come back to the project later only to forget what the correct measurements were, or to guess at which tests were successful and which prints were which. And similarly in software, I find it super helpful to document processes and functions so that when I come back to them later, or if someone else were to pick up the project, everyone would know what's going on. In fact, there were too many times where I was left scratching my head, looking at this new Hydra head that had appeared. Sometimes that challenge appeared because of me, and that's fair enough, I'll take that. And other times from something else. But something that would have really helped in either case was a version control system. With software, version control systems like Git are pretty ubiquitous, but I'm certainly not in the habit of setting one up for a small piece of code. And what happens if the project isn't code and instead is edited through a GUI program like Inkscape? Then I'd argue that it's still important to be in the mindset of always setting one up, because it allows not only for setting up backups, but more importantly, debugging when an issue would have appeared in my code so I can figure out where that issue came from. If you can't tell by now, I had done quite a bit of experimentation to be able to slay all of these Hydra heads, all of which allowed me to gain a deep understanding. And I was able to use that understanding to be creative with my next problem. You might have seen that the design consists of text, and while wood engraved text looked great, it was barely readable on acrylic. Wow, you actually can't see that. But what was very distinguishable was these scored lines. And now I had a dilemma. How would I go from these field characters to lines that can be scored? Well, you might not know, but fonts are technically filled paths. And you could say, why not score along the middle of a character? And I would say, sure, but to my knowledge, there's no software that does this, probably because it isn't easy. Like, look how badly my attempt worked out. And also, this is so hard that there's a market for single-line fonts. You can go and buy these because of the effort that they take to make. But depending on your software, they might not even work because your software might not know how to handle these open paths. And even doing so would mean that I wouldn't be able to keep the same font style. So what could I do? Well, instead of wanting one path, why not just remove the font's fill and score out the outline? At the size of the font that I'm dealing with, the font outlines are going to be so close together that it's just like having a single path. With the caveat, of course, that with two passes in one place, I'll cut right through. You can see it with a slash here. A slash is normally just a single line, but it goes up and then back down, and that's not going to work. But with all this understanding that I had, I can update the settings of the laser cutter so that it cuts with less power for these lines. And I know it's not the perfect solution, but it's good enough and shows how with a bit of pragmatism and understanding, a small hack can save some time. And after slaying that head, I'd gotten pretty good at this. I'd gotten so comfortable with the laser cutter that I realized that when I realized that I wanted a matte finish on both sides, which I couldn't easily buy, instead of achieving this with some sandpaper and elbow grease, I thought, why bother? I could just achieve a similar result with engraving. And so there I was, waiting for the result after having just setting it all up, only to find that while I got the look that I had wanted, I had also successfully warped the material, making it no longer flat or looking like a card. Which I later learned is expected when doing something like this. But can I really blame myself for trying? When programming, it's so easy to get away with overloading functionality out of ease of use, but I should know that I might not get the expected result. And so it would have been worthwhile to invest in a bit of time using the tool made for the job, regardless if that tool is sandpaper or a programming library. Now, let me explain to you another problem with acrylic. You might be able to see how I first started cutting from wood. It's great for prototypes, since it's generally a cheaper material that's easier to find scraps of. But prototypes aren't meant to mimic your final product, and as such, will have different properties. Laser cutters have to change the power and speed settings depending on the material, because, in case you didn't know, wood burns quicker than acrylic. But what this also means is that all the tolerances that we had set up before will also change. In fact, differently colored acrylics will act differently since black absorbs more light than white. And just like in software, a prototype is great for show, but not great in production, and thus we often need to redesign our system to support higher throughputs. Not to mention, while wood is easy to mark, unlike acrylic, acrylic is more brittle, causing the final designs to snap a lot more easily. Which brings me to the next thing I should have told myself: keep it simple, stupid. When I was first ideating, I thought, okay, I want 2 coins and 2 USBs and this and that, and I kept trying to think of more things to add to the card to take up all of this white space. But white space, as I found out, is important. It's what gives the card its structure and how it holds itself together. And similarly, my initial idea was to design my own cases for these USBs, but I was already dealing with all of the other issues, so why would I give myself more when the work was already done for me? Likewise, it's so easy to over-engineer things in software that it's just as easy to forget the benefits of first designing an MVP before later building everything else on top. And after that Hydra had been slain, alas, we're at the end of our adventure. Which I'll finish off by saying that there's very likely a makerspace near you. Look it up, give it a go, find a mentor, or become a mentor. A lot of the things that I learned or did, I couldn't have done without the folks over at the James N. Kirby Makerspace at the University of New South Wales. Because just like in programming, it's so welcoming to be unstuck by the help of someone else. I've open sourced a lot of this, so feel free to edit the design to your liking. Like, you probably don't want an Australian-sized coin hole. And while this might be my current final design, and this my final product, there's always more to do, and so many slain Hydra heads that I didn't have time for, and likely many more to appear. So come and find me if you had questions to ask, suggestions to make, or things to contribute. Anyways, I hope you were able to get a lot of takeaways, but in case you needed one more, I've made quite a few of these. So if you come and say hi, I'll make sure to give you a token of appreciation. I want to say thanks to my mum for inspiring me to do this, to fix this project, as well as my partner, friends, and you for joining me on my adventure. Thank you so much.